Hi, everyone. My name's Ross, and I'm a senior application scientist at Unchained Labs. I'll be your moderator for today's virtual seminar, and I wanted to thank all of you for joining us. We will have a Q&A session at the end of the presentation. To ask questions, all you have to do is click on the Q&A button in the Zoom navigation bar that's either at the top or the bottom of your screen, and then type in your question. We'll get to as many questions as we can after the presentation, but please don't submit your questions anonymously so that we can follow up with you later. Now, I'd like to introduce Kevin Lance, who leads product management for Stunner. Today, Kevin will take us through how new applications on Stunner can decode even highly overlapping ADC UV spectra without any prior drug linker knowledge, pulling apart the contributions from protein and the payload. We'll take a look at data on commercial and clinical ADCs and see what Stunner can do to make UV-Vis and DLS characterization simple, fast, and easy to develop. Now, I'd like to hand things over to Kevin. How's it going, Kevin?
Pretty good, Ross. Happy to see you today. Excited to talk about stutter.
Well, I'm excited to hear about it, so take it away.
Alrighty, I will do the share screen thing and let's go. So first off, thank you to everyone out there for joining my talk today on decoding ADC spectra for DAR measurements at warp speed on Stunner. I'm excited to get into it. I want to begin with how I think about ADCs. Well, they're great and powerful, no doubt. But also when you try to start to measure them for quantification and DAR by UV vis, reality is really not quite what you see in front of you. It can actually be pretty intimidating when you try to use those methods. So with the help of Stunner, today we're going to show how to pull back the curtain on the great and scary ADC quantification by UV vis problem and show you that really we can get some very cool things done and make ADCs not so scary. I want to begin by drawing an analogy to classic antibody analysis. In this case, we have two key questions that we'll be exploring today. How much do I have? Quantification, in other words. And we're traditionally going to do that for antibodies by UV vis since it's a nice, simple, fast method. On the other side of the slide, for sizing and aggregation, we're answering the question, do I have aggregates? Is my antibody the right size? Has fragmentation struck in my sample? We're going to answer those questions by dynamic light scattering, or DLS. So for classic antibody, that analysis is pretty straightforward and something that Stunner can do right out of the box. However, for ADC analysis, DLS is the same, thankfully, but UV-Vis gets much harder. Answering questions about how much do I have and what's my average drug-to-antibody ratio, or DAR, all of a sudden become a pretty big challenge, especially when you're working with molecules that might be brand new to you, and you need to understand what's going on with them, even though you don't have all the information available at your fingertips. This is where we bring in Stunner. With new applications that we're talking about today, Stunner is going to make it easy for you to get to average DAR information and protein quant information at the same time as gathering sizing and aggregation information through the combination of UV-Vis and DLS. All right, the nuts and bolts of how this works. So with Stunner, you have a 96 well plate in normal 8x12 format, but instead of wells, we've replaced each one of those with a microfluidic circuit. You load 2 microliters of sample into that microfluidic circuit with no sample prep or dilutions needed. And those 2 microliters will be read within that circuit through 2 fixed path length microcuvettes shown here and here. We'll take a closer look at those in a second. And Stunner is going to gather UV-Vis and, if you want, DLS information from those samples after you load them. If you're running 96 samples by UV-Vis, you can get all of this information in about 10 minutes. If you're adding on DLS information to your UV-Vis sample, you'll have it all done in about an hour, maybe a little bit less. Taking a closer look at those microfluidic circuits, here we can see exactly what sample loading looks like with the help of some fluorescein and a blacklight. In 2 wells, I've already loaded 2 microliters of fluorescein. And as you can see, to load another sample, you simply add in 2 microliters into that input well, and the sample wicks into the plate. I'm also showing this video in real time so you can see how fast it is to pipette, load, and have your sample be ready. Once you put your samples into Stunner, what will happen is that it will pump your samples into those microcuvettes for measurement. So on the left of this slide, you're seeing samples before they've been read, and on the right, you're seeing samples after they've been read. The two diamond shapes are the cuvettes for a single microfluidic circuit. And so you can see how in each one of these situations, one cuvette is brighter than the other. What that's actually showing to your eyeball there is that these microcuvettes have two different path lengths, which gives us a very wide dynamic range for quantifying molecules, in this case ADCs, by UV vis. It also gives us enough volume to do DLS right in those microcuvettes. The last thing I want to point out is because each one of these microcuvettes is independent, there's no sample-to-sample contamination possible, and because the sample is secure in your microfluidic circuit, you don't have to worry about evaporation, and your samples can be secure for up to 2 hours before reading on Stunner. Time to dive into analysis of ADCs. When it comes to analyzing DAR by UV-Vis, what has been out there for decades is what I'll call old school DAR. So this is a two-wavelength method where you could see the equations shown on the right of this slide. And the basic idea is that you measure absorbance of your ADC and you focus in on two wavelengths where you know the extinction coefficient for your drug linker, I should say, and you know the extinction coefficient for your antibody. If you know that those inputs, then running through these two equations with your measured UV-Vis information gives you average DAR values. In other words, if I know how much of my absorbance at 280 is coming from my drug and how much is coming from my antibody, and likewise at a second wavelength, in this case about 360 nanometers, I can do some pretty simple math and get to drug concentration, antibody concentration, and DAR. That's wonderful if I know everything required to actually run this math, specifically those four extinction coefficients. And that's where we start to talk about the shortcomings of that traditional old school UV-Vis method for drug-antibody ratio. If you have overlapping spectra, this math becomes much more complicated because it becomes much more complicated to know what your four extinction coefficients are. If you have overlapping spectra, having an unknown extinction coefficients, then you kind of have deal breakers for your old school UV-Vis method, which means that UV-Vis analysis needed more flexibility. So that's what we developed on Stunner. Using Stunner's ADC decode capabilities, you can take a look at your ADC absorbance spectra and decode it into its underlying drug and antibody spectra, even without any prior drug linker spectral information. In other words, if I'm taking trastuzumab and emtansine and I measure absorbance, I will get this gray line. If I'm measuring absorbance with ADC decode on Stunner, I know what antibody I'm running, in this case trastuzumab. So I have the trastuzumab spectra stored in Stunner's analyte library, its memory banks. Stunner will understand how much antibody is present in that absorbance sample and figure out that the remainder is coming from the drug. So this gives us a very powerful tool to analyze ADCs even when we have no a priori drug linker spectral information. Let's dive into that a little bit more. So once I've measured an ADC, the first challenge in this kind of analysis is trying to figure out what is the right antibody spectra and drug spectra when there's a range of possible answers. Here we're showing an ADC spectra in gray and the maximum possible antibody spectra as a blue dotted line. On the right side of the slide, we're showing the corresponding drug spectra, which would be the green dotted line. The blue dotted line for the antibody on the left is the maximum absorbance that's possible, since of course it can't go above the total absorbance for the ADC, right about in that region of the spectrum. And of course the right is the corresponding drug spectra. But in reality, the antibody spectra is likely lower and the complementary drug spectra higher. So here we're looking at what 70% of that maximum signal looks like. Or we could look at 50% of that maximum antibody absorbance signal. And notice how the corresponding drug spectra is climbing higher and higher as expected. So how do we figure out what the correct antibody absorbance value is within the range of possibilities? Well, we use Stunner's ADC decode application to figure out the optimized fit for the antibody spectra and the resulting drug spectra. Stunner's ADC decode application uses absorbance features related to tryptophan in the 280 to 300 nanometer region to determine the optimal fit and the optimal antibody concentration. So Stunner can use this spectra directly in the ADC decode application, or you can store it into Stunner's memory banks through a simplified store spectrum experiment. This means if I'm running simply a trastuzumab deruxtecan sample, like I'm showing on this slide, then I will tell Stunner to use the trastuzumab spectra that it's saved, and it can very quickly figure out how much deruxtecan is present, as well as how much trastuzumab is present in this sample. This kind of intelligence is ideal when you start screening ADCs across multiple conditions. In this situation, we look at an example of trastuzumab that we're conjugating to multiple drug linker compounds. For this case study, we'll look at emtansine, deruxtecan, and vedotin. In parentheses, I'm showing the cytotoxic drug present in each drug linker compound. So with 3 different spectra in my experiment, and they're adding unknowns to my study, that's going to leave me without much of a clue as to how to quickly screen and best to characterize this example. So it's time to look for some extra brain power. If I use Stunner's ADC decode brain to analyze the spectra, here's what it looks like. I first start with my 3 ADCs, where trastuzumab is my antibody, and I've conjugated my 3 drug linkers. And I get the resulting gray absorbance spectra for my total ADC absorbance. Run this through Stunner's ADC decode application, and I understand how much antibody absorbance is present, which is shown in blue, and how much drug absorbance is present, shown in green. Sounds nice? Let's go ahead and start to validate that approach. The first thing that we wanted to do was compare how well decoded drug spectra matched up when they should be identical. In this case, we're evaluating 2 ADCs commercially available, where the antibody is different, but the drug linker is the same, trastuzumab emtansine and nirituximab emtansine. If we run the experiment on ADC decode and extract the drug linker spectra, we can then normalize and overlay them. And in the middle of this slide, you can see extremely good agreement between the blue trastuzumab spectra and the green nirituximab-derived ADC spectra. So this shows us that the emtansine spectra that we're extracting from these experiments is consistent. The next step, of course, is to compare it to what others have done before us. So from the source cited at the bottom of the slide, we evaluated the emtansine absorbance spectra versus what's available in the literature, and you can continue to see really good agreement between what we're extracting across the 2 experiments and what's available in the literature, which is a great indication that ADC decode is working appropriately and extracting a correct spectrum. I also want to emphasize that when it's extracting these spectrums, this is the kind of thing that happens immediately. It's done by the time the experiment has finished its run, 10 minutes for a full plate for UV vis only, and you see the results shown here on this slide. In this case, we're going ahead and getting antibody concentration, and we know an extinction coefficient for emtansine, so we're getting a drug concentration and a DAR value as well. Next, we want to evaluate the performance of this approach for linearity, precision, and accuracy. Here we're looking at precision and linearity with a 1:2 dilution series across those 3 ADCs. The blue bar in this case is the ADC decode result, and the green bar is using Stunner's dual wavelength application to apply that traditional old school DAR analysis when we know all of our extinction coefficients. You'd expect them to agree if everything's working as it should be, and that's exactly what we see here, with very good alignment between the green bar and the blue bar across all dilutions in all 3 samples, drug concentration and antibody concentration. The other thing that we can see here is that error bars are overlaid on top of this, so you can see the precision is incredibly good, especially since we're looking at this in a log scale. You can also see kind of linearity, but what I've done to show that a little bit clearer is graph them slightly differently. So I've taken the same results, and now I'm simply dividing across dilution steps. So for my 1:2 dilution step, my 2:4 dilution step, and my 4:8 dilution step, if If I divide those results, I get these answers. If I'm looking at drug concentration or antibody concentration, I would expect a 1 to 2 dilution step to have a ratio of 2 in those results. So that's what I see going across these three molecules and all these dilution steps. I get very close agreement with that expectation that my antibody and drug concentrations are changing by a factor of 2. DAR, however, is not changing across my dilution steps, and it should be consistent at a ratio of 1, and that's indeed what we see. To evaluate accuracy, we wanted to compare these commercially available ADCs against their C of A's, which is determined sometimes by Hicks, sometimes by LCMS characterization. And we see when we're evaluating Stunner's performance by ADC decode to get you DAR answers, it's in good agreement with what we had provided on the C of A, within about 10% error. And I'm showing the same data on the left and graphed on the right here in this slide. There's also situations where I wouldn't have any molar extinction coefficient information available to me. In other words, there's no epsilon or E value that allows me to convert between drug absorbance through the extinction coefficient to get to drug concentration. In those situations, what Stunner will report is drug-antibody absorbance ratio, or DAAR. What Stunner's doing here is understanding, well, I might know the concentration of my antibody because that's typically understood, but it's not a requirement for this kind of assay. In that case, I can report the antibody concentration, but where I don't know all of my other extinction coefficients, indeed I know nothing about this drug molecule, I can still report the absorbance coming from the drug, the absorbance coming from the antibody, and report the DAAR, the antibody absorbance, drug antibody absorbance ratio. So this gives me a ratio in OD to OD that I can use to compare different conjugation conditions, process conditions, or any kind of comparison I want to make across multiple samples. Because OD will scale exactly linearly with concentration, it's a reliable metric that you can use as a proxy for DAR when extinction coefficient information is not available. But of course, with Stunner, it makes everything a lot easier. So if you want to get that molar extinction coefficient information for your drug, which will help you convert between absorbance and concentration, that's easy to do once you have a single known ADC. So in this case, we're taking a trastuzumab emtansine sample. We know in this measurement, we have an OD at 252 nanometers of 5.87. And then we know with this sample, because we run it through other analytical assays, that the average DAR is 3.8. Simple division at that point gets us, along with molecular weight, gets us to a molar extinction coefficient that we can then apply to any other ADC that's conjugated to emtansine. You can see how this might be useful when you're studying a panel of ADCs that might share the same drug linker molecule, but different antibodies or different linker sites. Lastly, for the last topic on UV-Vis characterization, this type of analysis is also something that you can expand beyond traditional ADCs to newer modalities. So here we're showing an ADC example on the left, but on the right we're showing an example for an antibody oligoconjugate, where we're understanding the concentration of the antibody, the conjugated oligo, and we're able to report an antibody oligo ratio expressed as how many oligo molecules on average are found conjugated to antibodies. So something that Stunner's set up with to study a wide range of conjugated molecules, which is extremely handy, especially as the world explores newer modalities. Besides all this UV-Vis information, Stunner's also going to report on the same sample, if you want on the same read, the size information for your ADC. So across those three ADCs that we studied for our case study today, you could take a look at size to confirm molecular integrity. In other words, everything is the right size and you don't have aggregation or fragmentation problems. And you can also spot those aggregates early on in your process. So for these three examples, trastuzumab emtansine and trastuzumab vedotin, my mass distributions show me that almost all of my sample mass is at the right size, about 10 or 11 nanometers diameter. However, for trastuzumab deruxtecan, I have a broader sample size distribution, and I may want to investigate that and try to optimize buffer conditions or storage conditions to reduce the aggregation that could potentially happen. So that's the story of Stunner and how it can help you analyze ADC and understand average DAR, protein quantification, and sizing and aggregation in a simple all-in-one biophysical readout. Hopefully, after seeing that data, you agree that Stunner will make ADC characterization and method development something that's no longer going to delay your ADC development as it strolls on down the yellow brick road. With that, we'll roll up to Q&A, and I'd like to thank you for your attention already.
Cool. Thanks, Kevin. That was a really informative talk. I enjoyed it quite a bit. You took us through how you can use Stunner to look at antibody concentration, to look at drug concentration, and DAR from just 2 microliters, and also get size and aggregation information from DLS. That's a lot of things you can get from a single instrument. So we've got some great questions that have already been submitted by the audience. And remember, you can still ask a question by entering it into the Q&A section of the Zoom navigation bar. You ready to answer some questions, Kevin?
Yes, let's do it.
All right. So first question, how long does Stunner take to perform measurements?
So if you're just looking at UV vis for quantification and DAR information, it takes about 10 minutes for a full plate, all 96 samples. Add on that DLS, and then each sample will run about 45 seconds to 1 minute per sample.
Cool. All right. And what's the concentration range that Stunner can use?
For this kind of ADC analysis, our recommended minimum is 1 OD at A280, so roughly 1 mg per mil, give or take, depending on your extinction coefficient. And that can be pushed down as low as 0.5 OD, depending on protein and drug absorbance and the precision you need to see in the assay. So it's sort of a precision question, I would say.
I see. Yeah, that makes sense. So more sample, a little bit easier to measure, but down 1 OD makes sense. So now you said that Stunner uses 2 microliters to run, but what's the dead volume?
Get this one a lot. So it just uses 2 microliters. 2 microliters go into the plate. That's all it needs. Everything else you get to keep.
Gotcha. Okay. Oh, I see. So another question that's come up a couple of times is you showed this for a couple of different, clinical ADCs, but could this work for other types of or other conjugates?
Yes, we've used this with dye-conjugated proteins as well. All you need is one component to have a tryptophan moiety in it and the other component to not. We're also still expanding our data set, and we'll start looking at other molecules and conjugate types.
Very cool. Yeah, on that front, how about, for example, antibody oligoconjugates? How would you approach those?
So these are actually easier cases for this kind of analysis to happen because nucleic acid absorbance is really well characterized and quite predictable. So you can simply tell Stunner, hey, I have an antibody here. I've characterized its extinction coefficient, and I have a nucleic acid. You could type in its extinction coefficient or type in its sequence, and Stunner's smart enough to do all the information, all the calculation for you at that point.
Very cool. So just a couple of pieces of information about the oligo and the antibody, and that's all it really takes.
Exactly.
Very cool. Now, we've got this from a couple of attendees, so I want to make sure we get to it. So, if you have a current Stunner instrument, will this new application work on it? And how would we go about getting it?
So any Stunner made since January 2024 has access to this information. That's the date where we did a sort of major hardware and software revision on Stunner's capabilities. So if you have a Stunner made since January 2024, you simply go to our website, go to the Stunner product page. You can request Stunner software from that. Or if you want, you can just simply email support@unchainedlabs.com. If you're covered by warranty or service contract, it's free of charge. And earlier versions of Stunner have access to the dual wavelength application only. So that sort of old school DAR method where you put in for molar extinction coefficients, you have access to that, but not the ADC decode applications.
Gotcha. Thank you. Changing questions a little bit from the ADC or from the DARs and concentration measurements to DLS. How would you deal with aggregation in the samples impacting absorbance? For example, highly turbid samples causing lots of light scattering.
Yes. So when you have a sample where aggregation has struck and struck quite significantly, how that appears in your UV vis spectra is turbidity. What we have in our ADC decode and ADC quant applications is the ability to unmix or deconvolute turbidity from the underlying spectrum. So it takes a look at the entire spectrum, it understands how much of a contribution turbidity is making, and it will subtract that out when it does its analysis. Raw data, of course, is also available to you if you want to take a look at that, but it eliminates it mathematically from the analysis, so you don't have to worry about that.
Fantastic. Um, so here's one of the another question kind of on how the ADC decode function works. So does the ADC decode application provide a concentration measurement if you don't know any extinction coefficients at all? And if, in those situations, what might you be able to do about that?
So for ADC decode to be able to extract the drug spectrum, it needs to know the antibody spectrum. Now, what I've played around with is sort of the sensitivity of this. If you have a trastuzumab antibody and you tell it a naratuximab spectrum, do things still give you some kind of a reliable answer? And the answer is yes. Now there's a little bit of variability there, but if you don't know anything about your molecule, you still have enough in the default analyte library to get some kind of answer at the other side. For the drug spectrum and the drug concentration, you do need the extinction coefficient to get to a concentration, but you will get the OD, and the OD will correlate exactly with the concentration of your drug. So you can compare OD to OD across any condition that you need to take a look at.
Okay, that makes sense. Now this question is a pretty broad one, so maybe it'll be a little bit easier to take it offline or talk to these particular attendees more one-on-one. But I wanted to ask because a couple of people have asked about it. Could you detail how the decode application works in the software?
So yeah, parts of this are something that we could talk about and describe. So for example, it is looking at tryptophan features in the absorbance. It's looking at that 280 to 300 nanometer region. And that's kind of the extent that we are going to describe with the ADC decode application. Um, and yeah, we're very excited about it. It works great for any kind of conjugate between a protein and a second molecule.
Cool. Um, so how about contribution from linkers? Do they tend to have any sort of contribution to the absorbance?
They can, and the way that this will work is drug linkers are kind of considered one thing. So especially as they tend to correspond one to one, you sort of treat them as the one intact molecule. So if they do contribute or they don't contribute, it doesn't really make an impact to the analysis, but they are kind of all analyzed in one group, I would say.
Okay, so for example, if you have, the same drug but two different linkers, it's possible that they would have different absorbance, but Stunner would be able to handle either of those circumstances and treat them more or less, or handle both of those situations.
Yes.
Okay, cool. All right. Well, thank you for your time, Kevin. Thanks for answering all of those questions. And again, thank you for such a great presentation. I learned a lot. I also want to thank everybody who joined us live today. If you'd like to have a deeper conversation with our team, please get in touch with us either at info@unchainedlabs.com or through our website, www.unchainedlabs.com. We'd love to connect with you. And thank you again for attending our virtual seminar, and I hope you all have a great rest of your day, including you, Kevin.
Thanks, Ross.